This is Jack Jackson back again. We're continuing our work of looking at compositions of isometries. In the last couple of videos, we looked at where there was a reflection first, and then that one had a lot of subcases because the positions of the mirror lines, how they compare to each other, uh, makes a difference. So that was the longest video of the four that we're going to be making here. In the last video, we looked at translations first, and this one we're going to look at rotations first. Um, One thing I want to point out here is this systematic looking at these with GeoGebra is just a way of discovering how these things work out. Uh, and then, I didn't know necessarily what all of these were going to be before I started, and I just worked through the different combinations of things to make sure I've got all the subcases and cases worked out. So here we are with our first translation. We can, our first transformation, which is a rotation this time. For this video, it will always be a rotation first, but in this activity, you can select reflection, translation, rotation, or glide reflection first, and you can select the second one over here. We can show lots of interesting related things here. So here we choose the center, and we choose the angle, and the angle is chosen by this here. Okay, it's in radians. Okay, so there we have our rotated image. Okay, what if the second one is a reflection? So we need a mirror line for the reflection, and then to get the final image, we take the intermediate image, the image of the rotation, reflect it across this, and just as I did earlier, this image of the first transformation, I use double primes, but the final image that we're getting is using the single primes. So the final image from A, it's rotated to A double prime and then reflected over this to get to the final image of A prime. Now, before we even start, I can predict possibilities here. Rotation is an even transformation and a reflection is odd. So we're going to get an odd transformation. That means it's either going to be a, uh, or let me put it another way. A rotation can be found by composing two reflections. Then we got a third reflection, the second isometry. So a total of three reflections. That could be a reflection or a glide reflection. So it's got to be one of those two. So the question is, how do we get from here to here? It's either a reflection or a glide reflection. I think it's pretty clear we don't quite have a reflection. What is the glide reflection? Well, one way to find that is to look at the line segments that connect up pre-image to image point. Let me see if I can make this a little less cluttered for us here. Okay, so if we look, these are these three line segments. Notice that they're, as I'm moving these things around, they're not necessarily parallel for sure, right? But if you look at their midpoints are all in a straight line. Well, that is going to be the line for your glide reflection. Okay, let's take away this one right now. So you get to here with a glide reflection. Okay, and the vector is going to here. So how do we see that? Well, one way we could see it is go ahead and connect up pre-image to image, find the midpoints, notice they're in a straight line, reflect the final image over that orange line that contains these midpoints. To get this image here, then your vector goes from here to here. So the glide reflection then is, I guess, is technically in the other order. It doesn't really matter. You glide first, then reflect. You could reflect first, then glide. It works fine. And so we get this intermediate image and reflect it over here. How do these compare to the original stuff? Well, here's the original angle here. And notice that the angle between the mirror line and uh, the mirror line for the second transformation and the mirror line for the resulting um, glide reflection have an angle between them, and that is half as big as that one up there. So that's an interesting thing. And once again, it contains these midpoints. Now, it turns out that if if the center of the rotation contains the mirror line for the reflection, then this is not actually a glide reflection. It turns out to be simply a reflection, which you can see there. So that's sort of a degenerate case. So you could get a reflection out of this. But if the center line here does not contain, is not on that mirror line for the reflection, center line for the original rotation, center point for the original rotation, and the line is not on the line, mirror line for the reflection, which is performed second, then you get a glide reflection. Okay, so that's kind of interesting. Okay, what if we do a rotation and then we do a translation? So there's a vector, and our final image is here. We can control this by, translating this anywhere we want. Now, before we start, I should configure this out. That's an even, rotation's even, so is even isometry. The translation's also an even isometry. We should get an even isometry here. So we should get either a single reflection, rotation, or not a sorry, let me say it right. Either a single translation, rotation, or identity. Which do you see? Does this look more, certainly not the identity, does this look more like a translation or a rotation? Yeah, I think it's a rotation. Okay, so let's see. One way we can find that is connect up pre-image to image point and look at these midpoints. Notice that these, if there's a translation, these would all be in the same vector, right? They're not parallel. They're not necessarily the same length either. The midpoints do not form a line, which would happen in a glide reflection, but their perpendicular bisectors do meet at a common point, and that common point is the center of our rotation. So the final image, if I take away some of this other stuff, is going to be a rotation about that point. Again, that point is where those perpendicular bisectors of those line segments meet. It's line segments connecting pre-image to image point. Okay, and we get a rotation there. Look at the amount of the rotation. It's the same as the original rotation. See, there's the original rotation, which was controlled by this, and this rotation is the same. Okay, so that's pretty interesting there. Okay, what if we do a rotation second? Okay, so the second one, we need a center for it. Well, let's do an easy case first. What if it's the same center? Can you guess what it's going to end up being? Well, the whole thing is just a rotation, right? But by the sum of those two angles with the same center, right? Okay. But what if that center, if that second center is not the same? Now again, a rotation and a rotation are both even isometries. They both can be formed by composing two reflections. So that's like you're getting four reflections. That's going to, an even number, so that's going to be either a translation, a rotation, or the identity. Clearly not the identity. And I think you can see it's not a translation either. So this is going to be a rotation as well. So there's the rotation here. How could you see that? Another way to see that is, again, connect up pre-image to image point. Let's just look at the original image, original, and then the final image. Connect up image and pre-image points. Find the midpoints of those, not in a line. Perpendicular bisectors, though, intersect at a single point. That's going to be the center of your rotation. Look at what happens on the angle here. This is the second angle. This is the first one. Look at the numbers here. If you add those two together, you get this angle here. Okay. So again, we're rotating. This is getting messy, but you rotating the original to get by this angle to get the purple one here. Then we're rotating it about this point over here, x prime, to get the final image. But we could have got it in as one step by rotating the blue one to the red one about this one right here. Okay. Finally, what if we have a glide reflection second? Okay, for a glide reflection, you're going to need a vector here for the glide. And then you're going to need a parallel to that vector. Reflect that over for your final image there. So let's see here. So now the question is, how do we get from here to here in one single transformation? Okay. Well, a rotation is even, glide reflection is odd. So we're going to get an odd isometry here. So it's either going to be an odd one. That would either be a reflection or a glide reflection. I think it's pretty clear in this case we're going to get a glide reflection. So how can we see that? Well, if we connect up pre-image to image points with line segments and look at the midpoints, they're in a line. That line is the line for the glide reflection. Reflect the final image over that line, you'll get the intermediate image from the glide reflection, and that will help you identify the vector there. So if we were to translate A by this vector here to this A quadruple prime, then reflect over this orange line here, we'll get our final image A prime here. Okay, so lots going on here. You can examine this some more if you'd like. I encourage you to get into the sketch, experiment into the GeoGebra activity, experiment with some different options there, and look at that thing dynamically. You can see what's going on. But let's summarize here now in a table. If you do a rotation first, and then you do a reflection second, where the mirror line contains the center of the rotation, you end up with a reflection. The mirror line will be the rotation of the original mirror line about the center of the rotation by 1/2 the amount of the original rotation. The mirror line contains midpoints of line segments from pre-image to their images. If you do a rotation first and then a reflection, the mirror line does not contain the center of the rotation, you get a glide reflection. The angle between the mirror line of the original reflection and the mirror line of the glide reflection is 1/2 the measure of original rotation. The mirror line of the glide reflection contains midpoints of line segments from pre-images to their images. If you do a rotation and then a translation, you get a rotation. The center of the resulting rotation is at the common intersection of the perpendicular bisectors of the line segments from pre-images to their corresponding images, and the angle is the same amount as the original rotation angle. If you do a rotation to rotation, it's the same center and the opposite angle, you're going to get the identity transformation. So the inverse of a rotation is a rotation about the same center with the opposite angle, same magnitude, but opposite sign or direction. Okay, so if you rotate it, 45 degrees clockwise, the inverse will rotate 45 degrees counterclockwise, same center. If you rotate and then do another rotation with the same center but not an opposite angle, you'll get a rotation. The center will be the common center of the two rotations, and the angle will be the sum of the original rotational angles. That's still true for the identity transformation as well. It's just that the sum then becomes 0 for the rotational angle. If it's a rotation followed by another rotation, not the same center, you still get a rotation. The center is at the intersection of the perpendicular bisectors of the line segments from pre-image to their corresponding final image points. The angle is the sum of the original rotational angles. And if it's a rotation followed by glide reflection, you get a glide reflection. And the mirror line will contain midpoints of the line segments from pre-images to their final images. So that gives you something there for rotation. Next we will do the last one, which will be glide reflections. We'll do those glide reflections first. We'll do those in the next video.